So hello everyone. Torbjörn Minde is my name. I have a long history at Ericsson, but now I am the head of data center research at RISE, Research Institute of Sweden. My last years at Ericsson, I was head of research strategies, and I've been in the research world for a long time. Started out as a researcher on neural networks, the early days of AI. So I will go through today a couple of things we see from Rice Research Institute for the future, the challenges that are ahead of us. And I will also talk a little bit about the use of AI, etc. So I represent RISE, and RISE Datacenter. We're a full-scale research environment, 25 employees, and we do a lot of projects in the field of data center, mostly facility-oriented, but we also have some infrastructure software activities ongoing around the edge. The unique things about us is one thing is our lab facility. We have 1,000 square meters of lab with a lot of different test rigs for air cooling, liquid cooling. We have wind tunnels, we have edge, we have small microgrids, we have climate chambers and climate boxes, etc., that we can play around with in different projects. We do both public funded research projects like EU funding or national funding, but we also do direct research to a number of companies. And we also have our own data center where we run GPU clusters for RISE AI researchers. We have got a number of prizes for our work, and the one I'm most proud of is the second place in the Best EU Project 2022. These are the official partners in our partner program, and as you can see, some Swedish companies, Ericsson, Vattenfall, ABB, and Meta. And then we have Vertiv and Castrol as well, and the university. A couple of not public yet partners as well involved. And we do then research project for these partners as well as public funded projects. Okay, I will start the presentation by talking a little bit about future applications that are possible to do now, starting to be possible to do, and this will drive the infrastructure for the future. I have very early, I bought these Google glasses. They were very light and nice, but the battery pack behind the ear and the computer, the little microprocessor there was not powerful enough. The screen was good, but there was no interaction really with on the world around you. But now I can see in front of me a lot of different applications where these glasses come into play. When you can talk to the application and ask, what is the house in front of me? It's Stockholm Central Hospital. What about the street name, Central Street? Things like that can be possible to implement today, and we will see this now with the new glasses from, for example, Ray-Ban. And it's going to drive a lot of compute because it's going to need to be compute in the close to the users. We call it edge, right? So in the network, for example, network edge, or even on the device. Another application that we have been working on together with partners is this. We have a autonomous flying drone in a mine. So when there is an accident in a tunnel in a mine, people are not allowed to go in there. Only rescue missions if there is persons in the tunnel. So that's the first thing to figure out, if there is a person that have problems in the tunnel. So the idea here is to send in a drone that do object identification throughout the flying time, and if there is a person laying down or sitting or something there, the drone needs to stop and the communication can be, if possible, communicate with the person or send in a rescue mission. So this will create a lot of AI compute, both training models for object identification and the actions needed for the drone to do this autonomous operation. So this is another example of a future application that will drive a lot of compute activities. And compute, we're going to see compute of these AI models, both for the training, model training phase, and that is in big cloud AI cluster, AI factories is called in Europe, in the background, and then the use phase, different places, a lot of different places. Maybe today it's mostly in a little bit more central locations, but we will see a lot of compute clusters in the network and on-premise that do all this inferencing close to the end user, so you have this fast response as well for the user experience. So that was a little bit of a kind of examples of what will drive the compute. As I can see it now, with the new type of AI models and the new type of 5G, 6G networks and possibilities for edge compute, we will see a completely new set of applications that has not been possible to do before. I just recently talked, as another example, to a startup that will use generative AI models to be able to help service technicians that see an equipment, and they can talk to the instruction book instead of trying to browse through it on the mobile phone. They can talk to the instruction book and find and maybe send pictures and get the right directions immediately, or actions, etc. So this will be a very interesting future. Applications can be used both for good and bad, of course, as we already seen. But then we have the thermal management of this infrastructure. And the sad thing about the CMOS technology, even if it's enabling a lot of things, the sad thing is it produces mostly heat. Most of the electricity coming in will produce heat, and if this was a light bulb, it would be banned. But this is the only technology that really works, so we need it. It's the foundation for all the innovation in the digital domain. So of course we need CMOS, but it is a lot of waste heat or excess heat out of the data center or the compute nodes. And then, of course, we need to think, okay, what is producing this heat? And the thing is that it is really the transistors switching that is producing the heat. So every transistor, when it switches, it will dissipate energy, heat. When it goes from one state to another, it dissipates energy. And as you can see on the left side, that's the prediction and the measurements of what the switching energy is for the different transistors, depending on the technology that is used. And today we are at about 10 attojoule. Attojoule is a really small amount. As you can see, a lot of zeros there. It's not even possible to understand. But 10 attojoule is what we see today in the most advanced CPUs and GPUs. And for the future, we expect around 2031 attojoule according to the prediction. So that are the two numbers that you need to have in mind. Switching energy dissipation. Today 10 attojoule, 2031 attojoule. And if you check that with the processors, GPUs, lately GPUs, you can do that, calculate the line, the unit length and capacitance, etc. And you will find out that the A100 GPU is 15 attojoule and the H100 GPU is 10 attojoule. So So it is the 10 attojoule number we can work with right now. So if you then try to calculate the total power of a GPU, you will, if you start with a 115 attojoule, you will, if you calculate the number of transistors and the switching frequency, you will get the power of the GPU. And then not all transistors are light at every certain moment. So you have some dark silicon, so you have to scale it with that. And then you have the die size, and then you will get the max heat flux, because that's the heat flux that is driving the cooling. And as you can see here, for the A100, we have 484 kilowatt per square meter. It doesn't say much yet, but I will show you a little bit in a while and compare it with different things. If you go and look at the H100 instead, you can see that with 80 billion transistor and the switching frequency of 1665 gigahertz, you will end up with, and the die size of 814 square millimeters, you will end up with a heat flux about 860 kilowatt per square meter, and that is 0.86 megawatt per square meter. So 0.9 megawatt per square meter. Another important number is this case maximum T-case maximum temperature of 85 degrees, and the T-case is the device, the GPU's case temperature. That's an important number because it's dropping down. So that is the H100 GPU at 860 kilowatt per square meter. Okay, and then if you try to calculate an imaginary microprocessor 2030 with 1 attojoule, maybe 1 trillion transistors, 4 gigahertz of switching frequency, you will end up with a thermal design power of 2000 watt, and the die size will probably be a little bit bigger. So you will finally end up with a heat flux of 1.6 megawatt per square meter. And the T-case temperature of below 60 degrees. So that is the numbers. And if you put those numbers then into some comparable, look what, okay, what is that compared to? You will find that, okay, the future processor is like a nuclear blast. So it's a nuclear power station. So that is the same heat flux for this small die as a nuclear power station, and it will be a lot of these GPUs on one server board, maybe 10 or more, and it will be a lot of heat flux. And as we know, nuclear power plants, you only cool with water, so we are going liquid cooling here. And you can even calculate, maybe these are very detailed, you can take a look at the slides later, and we have our scientific lead, John Summers, he can explain this backward and forward. But if I just summarize this analysis is for the H100 and GPU, and we can find out that yes, it is still possible to cool it with air, because the air limit is right there. And it's possible still to cool it with air. And of course, we at RISE, we have H100 servers, and they are air cooled. But you cannot fill a complete rack with that. That will be very tough. You need a backdoor, rear door heat exchanger, or something else to improve the cooling if you do that. But possible to cool with air. But if you start calculating the future processor, like this 2000 watt XPU, that imaginary one that we talked about with 1.6 megawatt per square meter heat flux, you will figure out that it's not possible to run it and cool it with air. You need liquid, you need targeted forced liquid cooling. So that is one conclusion for the future. And as we can see, the next generations of GPUs, they will come in racks, liquid cooled racks, as we already seen presented this year. So that was kind of the things that will drive the facility side of things, and then, okay, what will this mean for the future digital infrastructure? And the first thing we need to think about, okay, how much energy will be used by these type of algorithms? We did some calculation a year ago, and these numbers that we came up with, I can see it floating around in different presentations. And I think this was the first numbers that really presented outside the OpenAI and those that knew the numbers. Anyhow, we calculated if we try to train the GPT-4 model, okay, how much energy will it take? And as OpenAI said, they were using 25,000 NVIDIA A100 GPUs, that little bit older technology. They used 100 days to train it. It will take 100 days with this number of GPUs. And the cost is high. And the energy is high, 50 gigawatt hours. So that is a very costly model to train, but that was without optimization. This is a year and a half ago. A lot of work have been done to optimize all these algorithms. I have seen a lot of different proposals on how to make it more efficient. And the improved GPUs, of course, will also take the training time down and the number of gigawatt hours down. So it is per generation of GPU, it's maybe 2 or 4 times less energy for the same model size. And then we have the model improvements to optimize, make them sparse and maybe redo retraining and things like that. And we don't see now 50 gigawatt hours for this large model. It's much less. If you take a look at the inferencing, the use of these models, this is another calculation we did this year. And you come up with a number of each request. When we ask ChatGPT something, each request 1.5 years ago was 1.2 watt hours. And that is 4 times the Google search. But now with all the optimizations, probably dropped down to like a Google search. A Google search is also probably less, it's much more efficient today. So it's dropping down. So this and the number of gigawatt hours with 100 million users is about the same size as training the model. The use phase, if it's a lot of users, it will be about the same energy use for serving as for training. So this was kind of a summary of the calculations. And then, of course, you need to look at, okay, how many GPUs are there around in the world then? And this was just some numbers from Omdia I saw. And they presented how much GPUs were sold 2023 to the biggest customers of NVIDIA. And you can see Meta bought 150,000 GPUs, etc. So it's a lot of GPUs out there because this is just the big companies. And if you calculate just for these companies and try to calculate, okay, how much energy is that? It is 5 terawatt hours. Okay, how much is 5 terawatt hours? In Sweden, all data center in Sweden right now is about 4 terawatt hours. So it's similar to all data center activity in Sweden today. Maybe that doesn't say much, but this is a third of Irish. I think Ireland is around 15 terawatt hours or something like that. And you can compare that number to Amsterdam and Frankfurt, etc., and London, and see that okay, it's about the similar sizes, just this number of GPUs, and that has of course made a growth happening in the US, especially. We have seen reports on that, but But there is this is from a report from EPRI, and they have some surveys from 2020 to 2023, and it's really a little bit different results. So what they have done, they have a minimum result and a maximum result, and they have done some averaging here, and it seems like an exponential curve. We'll see when the numbers are settling down a little bit. It is an increase for sure, because we can hear about all the co-location spaces and the growth rate and the of data centers in the US right now, and it's starting, I guess, to spill over to Europe a little bit. But the future is of course interesting, and there is some estimations in predictions here in that report that you can read. There are some expert estimates, and there are different scenarios, and you can see that the scenarios range from 3.7 annual growth rate to 15%, and it would be a lot if it's 15% growth rate, annual growth rate globally. It's hard to believe that will be the case, but we'll see, because a lot of optimization is going on. Okay, so what is going to happen to the, just checking time, what is going to happen with the infrastructure then? Okay, if we just take a supercomputer of today, maybe looks like this. You have 8 racks here with 25 kilowatt per rack compute, and you have a 200 kilowatt CDU about, and 200 kilowatt UPS, liquid cooled, so it will be a row of equipment. You have probably seen that in a number of places. This is a regular supercomputer, I would say, HPC machine as we call them in Europe. And if you then try to put the numbers I've presented down in a table and compare it with the GPUs from NVIDIA, you will get the table like this. So you have the 800 machine GPU, 400 watt, H100, 700 watt. The one that is out now and the big companies are running, 1.2 kilowatt, called the Blackwell. And then we have the information about the Grace Blackwell GPU that will probably be around 1.8 kilowatt max power. And then you can see the teraflops that these GPUs do, and it's increase 10 times next year. Rack of Grace Blackwell, we do 10 times more teraflops than the A100, and as you can see, the training efficiency is also improving 10 times, and that will help the of course the energy efficiency. Maybe you train a little bit larger models when you get more energy, but this is the cost numbers that we will see. And then if you think about this and put them into racks, you will see that, okay, it will grow from 20, 30, 40. And we have heard that the racks, the reference design for the GPU, Grace Blackwell GB200 GPU, it will come in a rack, and I've seen them from a number of companies that have designed them, and they will be around 125 kilowatt, and it's all liquid cooled. And that will continue then if we just draw the line, the continuation. This table we did in the spring for a conference, and you can see it is growing from 1.8 kilowatt to 2.5 kilowatt, maybe to 4 kilowatt in 2030. And then we will have 1 megawatt racks in 2030. So these are crazy numbers. Will this happen? At least in this direction, and it will be all the liquid cooled. And we got this table confirmed by NVIDIA at DCD Connect. NVIDIA had this slide showed that the next rack with a GB200, they were going to be around 125 kilowatt, 130 kilowatt. And the next generation, and that's 2026, that's 250 kilowatt. So if you go back and look at, 250 kilowatt per rack, yeah, that's 2026 according to this table. So it seems like it's a kind of a linear prediction here to the future. So 1 megawatt racks, can we cope with 1 megawatt racks? How will it look like? I asked ChatGPT, how will that 1 megawatt rack look like if it is liquid cooled and integrated UPS, etc., etc. So this is the ChatGPT view on 1 megawatt racks. Maybe it will look like this in the reality. So it will be one UPS and it will be one fiber connectivity rack and UPS CDU for each rack of 1 megawatt compute. And the thing is that it will be very interesting to see how it will look like in the data center as well, because probably if you think about this, you will see that it is much more facility equipment compared to the IT server rack space. So the white space will probably shrink and the gray space grow. And this is just for illustration. I have no idea how exactly how many percentage, but just trying to indicate the direction. So the 25 kilowatt per rack row on the upper side is the one that you saw, I showed you, and the 1 megawatt rack is the ChatGPT picture I show you as well. Then I took these numbers and just trying to think, okay, if we would do it with current products, what would happen then? If you can look at this, I see the timing is leaving us, but if you look at this table, you will, for example, find out that, okay, you need 20 63 amps PDUs strips. And then you have to fill the whole outside of a rack with just PDUs if you would use today's technology. And you need a pump per rack that do 1200 liter per minute. It is not possible to do the way we do it. That is one of the kind of conclusions from this, that we need to rethink and start from the inner piece, which is the die that produces this heat flux. Start from there and rethink how we do this. Both the power in, the liquid in, the liquid out. And when you get the liquid out, we also need to rethink how we do the heat reuse. So heat reuse from liquid-cooled data centers is the next topic, of course, that will impact the infrastructure. So how are we going to do that? Can we exchange the heat pump with something else, with liquid cooling? That's a usual question. But the sad thing, the sad message I have here right now, the understanding is that to be able to run these GPUs, we need lower temperature, TK's temperatures. Below 60 degrees is the prediction by the electronic designers, and it seems to be the packaging technology that is the real problem, the heat spreaders, etc. So it will be really hot. A lot of transistors will do energy dissipation in a small space, and it will be difficult to keep cool. So maybe we'll not see the higher temperatures out of the liquid cooling equipment that we hope for. So we need to rethink the heat reuse as well. So these are the TK's maximum temperatures at different power and years. So you see that it will probably drop down to below 60 degrees. Seems like that if you listen to different electronic designers. And all this, of course, we at RISE are working with. We have our liquid cooling test bed, climate chambers, and emulators, and etc. to try to study all these questions, both direct to chip and immersion cooling. So these are the conclusions. See if my timing is perfect. So these are the conclusions. Very demanding applications we will see, and the new chipsets that we will see in the future will have heat fluxes like a nuclear reactor. So we need to do liquid cooling, and we will see out of this 1 megawatt racks. So we need to rethink, and we need to start thinking about how to do the heat reuse as well. We in this new world in the future, and we are working on it from RISE. Thank you very much.
Just 2 short questions. How are data centers addressing the increased energy consumption associated with AI processing, especially when they're trying to lower their carbon emissions? I know you've already touched on that throughout the whole.
Yes, I kind of touched on it now and then, but yes, it's a difficult question. They want both, but maybe you can. I was very kind of tried to put had a little bit more pessimistic approach at one of the panels I participated in some weeks ago. Everybody was so optimistic that it was possible to do both reach the sustainability goals and do this at the same time, but it will be tough. It will be hard work to do that.
Yeah, I think that's what we're getting from a lot of the sessions these last couple of days. And just one more question, if I can: is AI the perfect catalyst to ramp up district heating in the UK? Seen a lot of this in the Nordics, but seems right for UK, especially when we want to be more reliable neighbours.
No, I'm not sure, because we see, okay, right now, if we take all the equipment we have and do liquid cooling, we will see higher temperatures. You can see 45, 50 degrees out of it, but it will drop down, and then you lose that. And the district heating, I don't know if a data center is the perfect choice for district heating. Of course, if you have nothing else, if you have a bad coal heat plants or something else, if you have something else that you can remove out and take in a data center as the heat producer, yes. But data centers are not 24/7 heat producer. It's not year round, and it's not global. It's very Nordic. It's a challenging. If that could be the driver for district heating, no, I don't. I wouldn't say that. So, in some places, yes, but not in general.
Okay, thank you so much for joining us today, Tor. That was fantastic. Yes. Really, really great way to start off the day. Thank you.
Yes, thank you very much.
Have a great day. Thank you.